Welcome to June's Leetcode Challenge. Today's problem is Word Search 2. Given a 2D board and a list of words from a dictionary, find all words in the board. Here's our word search puzzle, and we're given a bunch of words, and we want to return an output of all the words that exist inside the word search. Each word must be constructed by letters sequentially adjacent cells, which means left, right, top, or bottom, and the same letter cannot be used more than once. Immediately when I saw this problem, I thought, all right, depth first search is probably the way to go. And it reminded me of the island search problem. And you could check for each word, the entire board, and check to see in a depth first search whether the word can be constructed or not. And that would work, but it's a big waste. Not only is it a waste of space, whenever you need to compare whether the prefix is existing for this word, it's going to be inefficient because you'll have to compare each letter. So is there a data structure that can help us out here? And they give us a hint that implementing a tree or a prefix tree would greatly help. So let's begin with that. And I'm not going to go too much into what this is because I've solved it before. But just know that it's basically a bunch of nested dictionaries for each letter of the word. That way, when we try to compare to see if we want to continue our algorithm, we could just search our tree instead. So let's begin by implementing a tree class. And we have first the initializer, which is just going to be, let's call it child, a dictionary. Now we want to insert a word. So first we'll set a current pointer and say this is equal to self.child. And for each letter in the word, we'll check, hey, does this exist? And if it doesn't, we'll create a key for this letter and then a dictionary for the value and continue on this algorithm until it ends. So for L in word, if L not in cur, then we want to say create a key with a dictionary like this and continue on. Say cur was now going to equal the cur of the dictionary. And finally, once we're finished, we want to mark the end of the word, and we'll do that by putting a hashtag here and just make that equal to true. Now we want to check to see if the word actually exists inside this tree. Okay, and that is pretty similar. We still set the current pointer to self.child. And for L in word, we're just going to say, hey, if L not in cur, then we immediately return a false. Otherwise, if it is, we'll just continue on like this. And at the very end, we're going to return whether the this hashtag is in the current dictionary. Return hashtag incur. So that should work. Now starts with is very similar, except we don't check this hashtag. All we're going to check is to see if we were able to finish our path, and if we were, then we can just return a true. So let's just test that out real quick. What we'll do is just create a tree, and we'll say t.insert ABC, and let's check to see if these work here. t.search ABC, that should be a true, and we'll check to see if AB works, that should be a false, and we'll check starts with AB, that should be a true. So let me just try running that, and that should be true, false, true. Oop, okay, so I got a runtime error. Let's see, starts with B. Name word is not defined. It's not word, it's prefix. Okay, so let's try that again. All right, so true, false, true. So that looks good. Now we have our tree structure. Okay, so now that we have that, let's first make some space here to make it readable. And what I'm going to do is take these words and put it into the tree. So let's first initialize the tree here and say for all the words in words, we're going to insert that into our tree. Now we want to write our depth first search algorithm, right? To begin that, let's first initialize a couple of variables. I'm going to start with n for the number of rows, and that's just going to be the length of board. M for the number of columns, that'll be the length of board 0, and also our output. We'll make that equal to a list. Now this is going to be a depth first search, and I'm going to pass the row, the column, as well as a built path. So I'm just going to call that path. You can call it whatever you want, but this is going to be a list, which I'm going to build up and check and convert it into a string when I check to see if this word exists. But what does this algorithm need to contain? All right, and for that, I'm going to go to the whiteboard. All right, so here I've represented the word search, and here's our tree. This is just going to be like a representation of it. And let's just begin at this algorithm. I'm going to start at the first cell, A. And the very first thing I need to check is, are we in bounds? Since we're passing in the row and column, we'll make sure that this cell actually exists, because otherwise our algorithm will break. So first, are we in bounds? And if not, just return and stop the recursive stack. But there is one more thing we need to check, and that's to make sure that if we are, let's say, A, B, we never want to go back to A, because we can't repeat letters, right? So in order to make sure for that, we'll have to mark somehow, just like the islands problem where we're going to mark it like 0 or something like that, to say that we've been here before. So we'll have to mark a visited somehow in this cell. But one difference with this is once we've finished this recursive stack, we want to revert it back. And that way, when like we go to D, A is not going to be visited anymore. So we'll have to make sure to have some sort of backtracking here. So I'll just write that. So once we're at A, now we want to check to see if we should even continue this, right? Because is A inside of our tree? And we have that function starts with to know whether or not the rest of the algorithm is necessary. Say we were at D. If we check to see if D starts with, and we immediately see there's nothing that starts with just D, then we should just end the algorithm right there, right? So if inbounds, if it's not inbounds and it's visited, then we want to return. But also, if it doesn't start with, not starts with, then we also want to return, because there's no point in going any further. Finally, we want to check to see, does it exist? Like we want to do a search. So say that we're at A, and then we just go down, A, B, it's inbound, it's visited, yes, and we're building up our string, and we check to see, is it inside our tree? And yeah, it is. So AB. So if it's in search, then we want to add it to our output, right? And I apologize for the messiness, but you might think, okay, then we can just end the recursive stack there. We can just return. But we can't do that, because there's actually other letters too that we need to check for, ABC and ABE. So we have to continue in our depth first search. It'll end once it's either out of bounds, everything's visited, or letters no longer start with like these letters. And that's just going to allow us to be like ABC, ABE. It'll stop once we see that it doesn't start with. And all the while, we'll be adding into our output the letters that do exist for the word inside our tree. And here, just our depth first search would just be typical, row plus 1, row minus 1, column plus 1, column minus 1, column plus 1. Yeah, so hopefully I'll code this out and it'll start to make a little more sense. now that we have our intuition of how we're going to code this out, let's start coding it. Very first thing we want to check, is it out of bounds or have we visited? Because if it is, then we just end this call here. So if the row is less than 0, or row is greater or equal to n, or column is less than 0, or column is greater or equal to m, or this cell has been visited before. So that we'll just try board, row, column, and I'm going to mark it with making these equal to 0. And if any of this is the case, then we just return, stop the algorithm right now. Great. Now we want to check for if it starts, because if it doesn't, then we should just end our algorithm, right? So if not t.starts, and I mentioned that I'm going to use a list for this building up this path. So let's first, how do we do this? We want to do a join for the path plus this board row column. And that's going to create a list with all of the characters, and we'll just call this string. And this is just to save on the expensiveness of appending strings and stuff. So let's see. If not t.starts with string, if the tree doesn't contain the starts with string, then you know what? Just end this right now, because why continue this algorithm? There's no reason. Otherwise, if we are able to pass this, then I guess we can do an else if t.search, and I should say starts with search string, then what? Then we want to add it to our output, right? So let's append it to our output string, and we can just continue on our algorithm. One thing to note is it is possible for there to be multiple ways to find this word, and we don't want to return duplicates. So I'll just say, okay, search and the string not in output. And there's probably better ways to do that, but it'll do for now. All right, finally, what do we want to do here? Well, look, we got to do our depth first search now, right? So what we're going to do is say row -1 column, and we want to pass in the path as well as the our built up path right here. And what I'm going to do actually is save it as a temp like this, just to make that a little bit more understandable, and pass in the temp. And we'll do our depth first search. Row -1, column -1, column +1. One thing to note though, I need to mark this point that I've already visited this point, right? So in order to do that, we will say, let's first have a placeholder for this current character. Like this. Now I'm going to make this equal to 0. And once we're finished with our stack, we're going to make that equal back to the placeholder, so that that's no longer visited. Okay, so that should be our whole depth first search algorithm. And we want to do this for each one of our cells, right? So for n in range of n, number of rows, for m in range of m, just call our depth first search. We'll do n m, and we'll just pass in an empty list for our path list as we build it up. And finally, just return our output. So I may be missing something here. Let's see if that works. Oh, got a runtime error. Name word is not defined. Word. Okay, and where is that? That is in line 34. Words. Okay, let's check to see if this works. Okay, so it looks like our test case works. Let's see if we can submit this. And there, accepted. Phew. So this is not the best solution. I already know that. But it is, I believe, a time complexity of n times m. There's probably some inefficiencies that I've missed somewhere here or there. I was able to avoid having to create like extra DP arrays for tracking the visited cells. But this works. Hopefully you guys can play around with it and figure out if there's anything better. But that's it.